Hello dear students, so this is Dr. Vijaya Babu. So in continuation with the previous lecture series of network analysis, okay, so we have done case 1 problem of nodal analysis, right? So in this lecture also we'll try to continue the case 1 problem of the nodal analysis. So this is a problem which is given, okay, so this is also a case 1 problem of nodal analysis. So how to apply nodal analysis for this problem to calculate the value of Vx. So this is the question now. Okay, so going ahead to solve this, I said you already. So try to redraw the circuit by removing the unknown things. Actually here unknown thing or the question requirement is the value of Vx, right? So we'll try to eliminate that Vx and we'll try to go ahead by redrawing the circuit as something like follows. Two amperes, 2 ohms is a resistor something like this, and 5 ohms, and it is 1 ohm, and then it is minus 1.4 amperes. Okay, so I have removed that Vx. Okay, now I can say this circuit is in my control. This circuit is in my control, so there will not be any ambiguity with Vx. So once you remove the Vx, okay, then the circuit is in our control, because now we can apply the standard procedure of nodal analysis for this problem. If at all if you continue with the Vx, the problem is you will be in compulsory in trouble. Okay, so that is why I said you to remove that Vx. Okay, finally once again you'll come back finally to calculate the Vx at last, no issues. Okay, so now I want to make the circuit is in my control, that is why I have removed the value of Vx, right? So going ahead now, so number of nodes, there are 3 nodes. I can identify you with the blue color. So this is A and this is B and this is a ground node. So all this point is C only, right? So all this point is C only. So this is everything is connected with a conductor. Conductor is a equipotential body, right? So that is why it is everything, the potential is C only. Now after getting these nodes, one nodes you must take it as ground. So that means the node Vc you try to consider it as 0 volts, which is a reference node. So this is I'm making it as ground. Now let us consider the potentials at the nodes A and B as Va comma Vb. Va comma Vb are non-reference nodes. Non-reference nodes, right? So going ahead now, so Vc equal to 0 and Va comma Vb non-reference nodes, right? Now these non-reference nodes Va and Vb, so now our calculation to calculate Va and Vb using what? Using nodal analysis, right? So I'm applying the standard procedure now. I'm going ahead, so I'll try to take the green color to fix the branch currents. So I'll try to fix the branch currents now. So first of all, let us fix this current as I1. So is it required? Is it required to take it as I1? So it is not required, because already you have a current source connected in that branch. So this is why take the advantage of it and just you take it as simply 3.1 amperes is entering node A. Okay, so now take the current, branch current through 2 ohms is, take it as now this as I1 now. Okay, and this current as I2 and this current as I3, and the last branch, is it required to take the branch current I4? So not required. Okay, so because already you have a current source now, take that advantage, take it as minus 1.4 directly. Okay, or else you can change the direction of it and you can take plus 1.4, anything is fine. So take as it is, why to worry with this? So take as it is, so try to take it as simply minus 1.4 amperes going out. Okay, so now I have fixed the branch currents. Now what is the next step in the procedure of nodal analysis? So applying KCL at node A. You need to apply KCL at node A. So what is the KCL at node A? 3.1 is entering is equal to both I1 and I2 are leaving. Okay, Now apply Ohm's law. So 3.1 is equal to I1. I1, this potential is VA and this potential is 0. So you can write I1 as VA minus 0 divided by resistor 2 ohms. Okay. Now plus the value of I2. So I2 is VA minus VB divided by 5. Okay. Now you'll try to multiply throughout with 10. This is the best procedure. Or else you can take LCM and you can do some mathematics. So instead of doing that, okay, what I am doing, just multiply the equation with 10, because LCM of 2 comma 5 is 10, right? So multiply with 10. It is very easy. So that means 31 is equal to, so multiplying with 10 means 2 is gone now. So we are having 5 of VA plus, here 5 is there means 2 of VA minus VB. Now directly I am writing the equation. So 5 VA plus 2 VA, it is simply 7 VA, okay, minus 2 VB is equal to how much? It is 31. Take it as equation 1. How many unknowns are there? Two unknowns are there, VA and VB. But here you have only one equation. So it is not possible to solve for VA and VB. That means you need one more equation now. So how to get the one more equation? So you will be getting the one more equation simply by applying KCL at node B. So how will you apply KCL at node B? You stand there and check the currents entering in and the currents going out. So that means entering current, you take it as I2 is equal to, okay, leaving currents are I3 minus plus minus 1.4. Okay, so that means here if you clearly observe the KCL at node A and KCL at node B, for KCL at node A, I2 becomes the leaving current. KCL at node B, I2 becomes the entering current. So hope you understood the logic. Okay. Now, so I2 is equal to I3 plus leaving current is minus 1.4. So now you apply Ohm's law on I2 and I3 and represent I2 and I3 in terms of nodal voltages. Right. So what is I2 now? I2 is simply VA minus VB divided by 5 is equal to, okay, I3. So what is I3 now? I3 is VB minus 0 divided by 1, then minus 1.4. Okay, now so try to multiply with 5 throughout. Then what will happen? VA minus VB is equal to, okay, so 5 VB minus 1.4 into 5. It is how much? 7. So from this, VA minus 6 VB is equal to minus 7. VA, taking this 5 VB left side, so we are having minus 6 VB. So VA minus 6 VB is equal to minus 7. So this is equation number 2. So two equations, two unknowns. So upon solving 1 and 2, okay, so the values of VA and VB, upon solving the two equations, equation 1 and equation 2, you will be getting VA is equal to 5 volts and VB is equal to 2 volts. Okay, so solving, I think you can do it using your calculator, or else you can follow normal methods, equation solving methods, or you can apply Kramer's rule also, no issues. You will be getting the value of VA as 5 volts and VB as 2 volts. Okay, so once you got the nodal voltages, so first what is given? Calculation of VX is asked. So I have erased that VX. Now take the circuit in your control. Then you fix the branch currents, you applied KCLs, you applied Ohm's laws, then finally you got the nodal voltages V and VB. Now you go back to the problem now. Okay, because our calculation is what? Vx. So if you clearly observe, I am going to the original problem now. So in the original problem, if you clearly understand, this potential is VB and this potential is 0 volts that we have taken, right? So that means I'll try to redraw the circuit now. So this is 1 ohm. So this is minus plus Vx. So this potential is VB and this potential is 0 volts. Okay, so from this thing directly you can calculate the Vx. So actually Vx is connected to negative terminal of the negative terminal of Vx is connected to VB, right? So that means I can say simply Vx is equal to minus VB. However you calculated VB na, substitute this. So finally Vx value you'll be getting it as how much? Minus 2 volts. So this is how you can solve the problems of network analysis. Okay, so the important thing what I have done is, dear students, I have erased the value of Vx or removed the value of Vx before starting the nodal analysis. And I have took the circuit in my control. Then I have solved for nodal voltages V and VB. Then once again I finally go back to the original question what is being asked, that is the calculation of Vx. And then however Vx you can easily calculate using nodal voltages. So once the nodal voltages are known for any problem, okay, you can easily calculate any branch current, okay, or else any voltage drop across the resistor, or else any power loss or power drop across the resistor. Anything you can do, right? So yeah, so with this I am concluding the case 1 problems of nodal analysis. So slowly we'll try to enter into the next cases or the complex problems of nodal analysis. So if you really like the videos, just subscribe the channel and like, and also your comments are really welcome so that they will encourage us in making a lot of videos on networks. Yeah, thank you for giving this opportunity today, students. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.